As promised, here's a differential equation in which the characteristic equation has complex numbered roots. So it's y prime minus 4y prime, y double prime minus 4y prime plus 13y equals to 0. Our characteristic equation is m squared minus 4m plus 13 equals to 0. And this one can't be readily factored, so I'm going to use the quadratic formula. Remember, the quadratic formula is, it's usually written as x. X is minus b plus or minus the square root of b squared minus 4ac over 2a. In case you've not quite sure what it was. So up here I'm solving for m, not for x. So anyway, let's use the quadratic on this one. Then m would be minus b. B is negative 4, so it's minus negative 4 plus or minus the square root. B squared will be minus 4 squared minus 4 times 1, 4a, times b, which is c rather, minus 4ac, minus 4 times 1 times 13. All divided by 2 times a, so that's 2 times 1. So let's see what we got here. This is, the negatives cancel. I have 4 plus or minus the square root of 16 minus 52, all divided by 2. 16 minus 52 is negative 36. So we have 4 plus or minus the square root of negative 36 over 2. Now, what's the square root of negative 36? It's 6 times I. The square root of positive 36 is 6, but with the negative inside it makes it 6i divided by 2. And then as you can see, we can divide 2 into both terms to get 2 plus or minus 3i. So I'm going to write this up here. M is equal to 2 plus or minus 3i. There we go. And then I'm going to erase all this and finish up the problem. The roots of the characteristic equation were 2 plus or minus 3i. So if we use the pattern we've developed, then my solution y is going to be c1 e to the 2 plus 3i plus c2 times e to the 2 minus 3i times x in each case. Sorry about that. Let's put those x's in there. Alright, now it's correct. And so really it's c1 e to the root 1x plus c2 e to the root 2 times x. Now we can fiddle with this. It's not a terribly useful answer for the real world. And so let's see what we can do with it. This would be c1 e to the 2x times e to the 3ix. So if I multiply the x through here and then broke that up, notice that if I combine these terms together, I would end up adding these exponents. 2x plus 3ix would be exactly this, 2 plus 3i parentheses x. And then I'll do the same thing over here. This will be plus c2 e to the 2x e to the minus 3i times x. There we go. Now we can factor out a e to the 2x. So I have e to the 2x parentheses c1 e to the 3ix plus c2 e to the negative 3ix. Now I'm going to go through these motions. There actually is going to be a pretty fast way to just write the answer from the characteristic equation, but I'm going through all the mathematics to justify it. So the good news is that you're not going to need to go through all this rigmarole. That once we learn the pattern, then we can just take this and write the answer. But that's what I'm developing here. Now at this point, I need to bring in Euler's formula. And remember, Euler's formula says that e to the I times theta is cosine theta plus I times sine theta. So there's Euler's equation. And instead, I've got I times 3x and I times minus 3x. So if I apply this formula to these terms here, I have e to the 2x, and I'm going to make this a bracket. My first term is going to be c1 parentheses cosine 3x plus I sine 3x, and then plus c2 parentheses cosine negative 3x plus I times sine negative 3x. Alright, so getting kind of messy here. Now, here's the good news. Cosine is an even function. The cosine of 3x is the same as the cosine of minus 3x. If you don't believe it, think about what cosine looks like on the unit circle. Cosines are the x-coordinates on the unit circle. So here's the cosine of, we'll say theta, would be this x term right here, and the cosine of minus theta would be the same x term. And so I can literally cancel the minus sign inside the cosine, and which means that I have two of these together. So I have e to the 2x bracket c1 plus c2 times cosine 3x. Alright, so that took off this term and this term combined together. Now sine is opposite because the sines are the y values, and so the sine of positive theta is up here and the sine of negative theta is down below. So when the minus is inside the sine function, if I were to cancel this negative, I've got to, in this case, bring it out front. So in the cosines, the negative just dies, and the sine function, the negative gets factored out. And that gives us plus I parentheses c1 times sine 3x. So I'm going to write c1 and then minus c2 times sine 3x. Alright, it's messy enough there. Now here's some more good news. I'm just going to rewrite these constants. c1 plus c2, I'm just going to call it c1. That's a constant. And I times c1 minus c2, I'm going to rewrite that as a constant, c2. So they're both constants, even with the I in it. Now who's to say that these c1s and c2s, as originally stated, are not complex numbers? Okay, so I'm just going to throw it all together. It's a constant. The constant might be imaginary, it might be real. So I'm going to rewrite the answer here. So let me make some room. We'll write the answer. So we arrive at this by bringing all this up here and kind of cleaning it up. The solution to this problem with these two roots is e to the 2x parentheses c1 cosine 3x plus c2 sine 3x. So notice what happens here. The real part of the solution ends up being, in this term here, e to the 2x. And the imaginary part, or at least the coefficient of the imaginary number 3, ends up being part of this 3x that we see in the cosine and sine functions. So there we go. That's a different way of writing the answer without specifically using complex numbers. Now, could it be that c1 and c2 are complex numbers? Well, in practice, I don't believe they are, because we don't have initial conditions that are complex. So it turns out if our initial conditions in these problems, for example, if y at 0 is equal to 2 and y prime at 0 is equal to 3, just throwing numbers out, you'll be able to solve for c1 and c2 with real numbers. So there's a solution. Again, look for the pattern here. The real part goes here, and the imaginary coefficient, the coefficient of the imaginary term, 3, goes in the cosine and sine. Now I'm going to do one more video on the complex numbers because there are actually two other ways to write this, and so I'm going to try to generalize that in our next video.